Hello. Hello.
Yes.
Hello, sir.
Hi. So can you hear me properly?
Yes, sir. Sir, your volume is a bit low, but we can hear you clearly now.
My volume is a bit low. Is it?
Now it's okay. Now it's okay, sir.
Now it's okay. So yeah. So before we start today's class, please tell me any doubts, questions that you have on anything that has been done so far. So your assignment is due tonight, right?
Sir,
Or
tomorrow night.
Tomorrow night. Okay. Yeah.
Sir, I had a question regarding the seventh one.
Yeah.
So, in the one where you have asked us to k-sort the array, so you have given us two parts to the question and to find algorithms of two different time complexities. But my question is, if possible, if we could find one which is faster than both, then could we give the same one in both of them?
Sure, you can do that.
Okay, sir.
Sir,
Yeah.
sir, I had a doubt in the fake coin question.
Right.
There is no explicit mention of what is the mechanism to like what is the basic function that we can use on this setup. Is it a comparison of two coins, or is it a weighing balance kind of
It's a
setup?
weighing balance thing.
So if we were to compare a sum of some coins and the sum of the other, that
Yes.
would be considered a single step.
Yes.
So that's as an order of one step then.
So you can basically put, say, 5 coins in one side and 5 coins in the other side and do it. I mean, you can say, what happens if I put 5 coins in one balance and 6 coins in the other balance? You can do
Right.
that. But because I have not told you how much the weight of the fake coin is, right?
Right.
So you will not be able to make anything out of that.
Sir, so it's a weighing, it's a balance, right? Not a weighing machine.
It's a balance. It's not a weighing.
Okay.
So, sir, what we have here is, I mean, it's not a. If we don't have to think in terms of writing it in code, right? Because this
No,
whole
you can
operation
explain.
will be.
You can explain it. You can explain in words. That's fine.
No, sir, but I'm asking in terms of the time complexity. Would this one weighing be an order one step, or in terms of
order
code
one.
that would be? Okay.
Order one step. One weighing is order one step. Irrespective of how many you put in one side.
Right.
One weighing is one step.
Okay, sir. Okay.
Yeah. So, some other questions? Any other questions? Okay, so if not, then I will maybe continue with whatever we were doing in the last class. Yeah.
Sir, can I ask one more thing? Sir, in the last class, there was a statement, like we were talking about some recurrence relation.
Mm-hmm.
And it was something like T of n is equal to 8 times T of n by 2 plus order of n squared. And there, if I'm not wrong, you would consider that order of n squared as a constant term in some sense. Although it's not really a constant term, but you treated it as a constant term, right? Sorry, sir?
Can you just repeat what you're saying?
Sir, in the last class, we had a recurrence relation of the kind T of n is equal to 8 times T of n by 2 plus order of n squared.
Yes, I didn't treat it as a constant term. It is actually order of n squared.
Right, but sir, is this in this setup it would be inconsequential, right?
Which setup?
Sorry?
Which setup?
In this recurrence relation, with respect to this, if this was order n or order n squared or order 1, it would still be the same solution.
No,
right?
of course not. It is okay. Maybe you are right. Maybe. Yeah, possibly you are right. Yeah. I mean, even order one will be the same thing in some sense. Possibly. Yeah.
So I was wondering whether this is some practice where we are able to make out what terms are inconsequential or with respect to some.
So there is so no, there's nothing like that actually, whichever inconsequential or not. So one thing that I have not told you guys, there is something called so you can see what I'm writing, right?
Right.
Yeah.
Yes, sir.
The asymptotic notation thing that I kind of explained and all, right?
Right.
Whenever you solve, I mean, that is something you have possibly seen it already. So when you solve a recurrence relations, okay, then there is something called the master theorem. Now, there's honestly speaking, I don't like this master theorem, so I'm not even going to explain you what is it.
Hello, sir.
It
Yeah.
has been discussed in one of our TA sessions, that Friday session.
Okay, you have been discussed. So basically, it's a kind of a black box kind of stuff like that, or it's a sure. It's a, yeah, I mean, like, what if somebody gives you something like this, something like this, then what is d of n? You can easily out. But honestly speaking, this is pretty cheap kind of a theorem to kind of. So this theorem will not work for various other things. So yeah. So as such, by looking at this expression, it is not that easy necessary to understand which one is. It's not inconsequential in some sense, to some level.
Sir, I think so. Your sound is very low.
So my sound is very low. Okay, somehow I'm on my headphone is not working, and if I put the headphone, I will not be able to hear. Let me just see what I can do something better. Hello. Hello.
Yes, sir.
Oh. Hello.
Hello.
Hello. Can you hear me?
Yes, sir.
Yes, sir.
You can hear me now, right? Is it better?
Yes, sir.
Hello. Is it better?
Yes, sir.
Okay. Okay. So yeah. So anyway, so coming back to this thing. Yeah. Yeah, so it is not very easy to kind of just pinpoint which all expressions are hard to rule out kind of stuff like that.
Okay, sir.
Anyway, so yeah. So some other questions? Any other questions? Okay. So if not, let's go to this kind of graph algorithms thing. Okay. So we were doing graph algorithms, right? And in the graph algorithms, what did we do? We kind of talked about how the inputs can be given. So the input can be given as an adjacency matrix or adjacency list and so on. And what we told is that one of the most important actions of graph is, of course, to check things like, is the graph connected, or is there a path from U to V, or what is the shortest path from U to V, and so on. So this is one of the most basic questions. Okay, so is G connected? Okay. Now this is a question that we will try to answer in today's class, and this is something not only will we be able to try to answer it, but we'll also see later on how this can be used for some other problems. So in the Friday's class, in the tutorial, so I assume that you guys were explained some amount of stuff about how graphs can be used to model various questions, right?
Yes, sir.
Yeah. So,
Yes, sir.
So did he talk about kind of this ordering kind of stuff like that, the topological sort?
Yes, sir.
He has done that, right? So I mean, so today we will see that how this topological sort.
Sir, actually,
Yeah.
we were just shown the context of where it could arise.
Yes,
but
yes,
we
I
didn't
understand.
discuss
You
much.
just shown the context of it to that, right?
Right.
Yes, sir. We haven't done the algorithm.
No, you have not done the algorithm. You have just seen the how a problem or an instance where a real life application of topological sort can be converted into a graph context in a directed graph thing, right?
Yes, right.
Yes, that's all. No algorithm here. I completely understand. Okay. So we'll come to that by the end of this class. So by the way, so let me start with asking you guys, what happens? Like, how many times have you guys gone to this, when you were a child, we used to play in maze, right? You know this maze, where there's like a, or in Hindi is called Bhul Bhulaiya thing. Have you guys played
Yes.
there ever?
Yes, sir.
So what is the biggest problem that you face? See, your friend has gone and hiding inside the maze, and you are trying to find him or her. How are you going to do that?
So we try different possibilities and try to remember the things that we have already tried and just don't do that until we get the answer.
Exactly. So you try different possibilities, right? To kind of go and search the whole maze, every corner of the maze. But the biggest problem that you always face is that you have to remember which all places have you already visited. You don't want to revisit the same place multiple times, right? So that is the most important thing. So somehow or other, you have to mark those places. So if somebody had given you a chalk in your hand and told you, okay, go and find out, then you have marked those places. Okay, this is something I have done, or this I am done, or this part is completely checked out, right? That is all that I'm going to do in today's class. How you can, if not only today's class, maybe also tomorrow's on Thursday's class also, that how can you visit the whole graph in a systematic manner, so that when you are visiting a particular vertex or a part of the graph, you can mark it accordingly so that you don't revisit the same thing again. So this is what is called graph traversal. Okay. So all you do is that you kind of look for all the vertices of the graph. You have to visit all the vertices of the graph. Okay. And but at the same time, you don't want to revisit the same vertex multiple times, because then that would be like that'll be way too much costly an affair. So there are two different. So there are various ways of doing it, by the way, but there are two different ways of doing it. One of them is called the depth first search, and I will explain it both in the. But has this thing done in your graph theory course in your district now?
No, sir.
They call depth first search and the breadth first search. DFS and BFS. Now, I can give you this context more from the point of view of, okay, of your say, study techniques. Okay, let's see. Okay. Say you, so in this semester, what all courses do you have? You have this algorithms, and what else other things do you have?
So parametric inference,
Okay,
linear models,
okay, and
sample survey,
okay,
and ecostat offstat demography.
okay, very good. Now, are these subjects kind of connected to each other? I mean, is this something that you do here is also required there in the later part of the thing? There are a lot of these kind of common things. Just give me 1 second. 1 second. Call something. Hello. Sorry, you can hear me, right?
Yes, sir.
Yeah. So whenever you study them, right, there are lots of common topics that are there. Correct.
Yes.
So you can think of them as modules, like various modules are there. Like then maybe some of the modules are common to both of them, or some of the topics are common to both of these subjects. Maybe it will be covered in both of them. Now, when you try to, when your end of your semester is to study everything, all the 6 subjects that are there, right? So in some sense, you can think of that there's a graph of topics, right? And I have to cover all the topic areas. Now, you can do it in 2 different ways, right? One is that you can, okay, let me start with maybe algorithms for now. Okay, I will first study the whole of algorithms. I will go in details of algorithms, understand the algorithms, whatever is going to be covered in this whole semester, study it and done. And once I'm done with algorithms, then I will go to the next topic. So which one did you say? I forgot. Say non-parametric inputs, right? And you pick that one up and you start to study that. So maybe some topics have already been covered in algorithms while you are studying that. Maybe some of them are not, or vice versa, and you do that. So you kind of, when you are studying a topic, you are going in depth into one topic. Okay, you're finishing off everything that is to be studied in that semester, in that topic, retracing back your steps, and say, okay, now I'm here, I will take the next topic. So that is kind of the intuition behind depth first, or depth. The other one that you can do is you say, okay, I will study all the topics, whatever has been covered in the first week. Then I will I'll go to all the topics that have been covered in the second week. Then I'll go to all the topics that are covered in the third week. So I'm not going and finishing off one particular area completely, right? But I am doing it one step at a time, but I'm moving at all the subjects together. So you're moving at a kind of a depth way. Breadth way. You are kind of ensuring that your breadth is good. So this is the intuition. If you can keep this one in mind, then maybe this will help you to kind of remember what is these 2 different things that are there. Depth first search and the breadth first search. So in the depth, therefore, in the depth first search, what we will be doing is that we'll start from a vertex. So you are given a graph G and a vertex, say U, which is the kind of starting vertex. So sometimes we call it as a starting vertex or a root. Okay. And with U, you can look at it, of course, you will look at its neighbors. Okay. And then you say, okay, I've looked at my neighbors. Now, how do I do it? In the case of breadth first search, you say, okay, is there a neighbor of U? If there is a neighbor of U, I go to that step. Then if I have the neighbor of U to, so neighbor of V, then I go to the next. So like.
Sir, what have you written after the arrow from U? Starting
Vertex. It's the starting vertex. You start your traversal of a graph from a particular vertex, right?
Right.
And you start from the starting vertex. Let me give you an example by some slides, okay? So this is this depth first search. So don't look at these things that are there in this side for now, okay? Let's not look at it. Let me first go over of the example. So this is an example of a graph, and let me first try to understand how we are going to cover this graph. Okay? And once we finish that, I will see how we can do the bookkeeping, kind of the mark out all of it. Okay? So to start with, so we say we start from this A, the vertex A, that is our starting. So what we do, so remember it's the depth first start. So our goal is to go in depth. Take any route and go in depth as far as we can go. So we look at its neighbor, any one neighbor, and say, okay, P is this neighbor. Okay, I go to P at this point. Then I said, then I don't go back to A. Then I say, okay, now I am at B. What is its neighbor? You pick any one neighbor of its. Okay, E is a neighbor. Fine. I go to its neighbor, E. Then I am at E. Then like, okay, now what is its neighbor? Okay, C is its neighbor. One of its neighbors, C. Then see, I'm not even stopping. Okay, I'm just keeping on going. At C, what is its neighbor? C has a neighbor B. But this B is something that I have already kind of visited. So, okay, so C has a neighbor B, but I am not too much worried about B. Does C has some other neighbor? But I can go. So, yes, C has a neighbor H. Okay, I am at H. See, I started from A, I walked down, I kind of found out H. I kept on going. Now, here at H, does H have a neighbor? No, H doesn't have any. So at this point, I've come to the end of my route. That there is no other neighbor of H that I can go to. So at this time, it's something like the whole graph that can be reached from H that has been completely been exhausted. I've looked at it. So okay, so now now I'm leaving H. So I will mark H green and I go back to C, the previous one that I've been. Okay, the C has some other neighbor. So now I'm retracing back because I've hit the edge. I'm retracing back my path. Okay, I come to C as does C has a neighbor? So C already had a neighbor B and a neighbor B that was been checked out already, and it has no H that has also been done. So I'll okay, C doesn't have any other neighbor. C is also clear. So in that case, I will say okay, so the C is also done. I'm going to the parent of C or the vertex from which I have come, which is E. At this time, I say okay, does E has a neighbor? Okay, now here I have done that route. I have completely exhaustively searched out this route. But now I'm seeing that does E has a neighbor, some other neighbor that is not looked into, and this is yes, E has a number, which is F. Okay, very good. Then I will come to F. Does F has a neighbor? Yes, F has a neighbor D. Now at this point, I will see that okay, does D has a neighbor? So first I will see that oh, D has a neighbor A, but A is already, I have already visited A. Does D has a neighbor B? I have already visited B. Does D has a neighbor? Yes, it has another neighbor E. I have visited E. So at this time, all these neighbors are completely checked. So there is no other place I can go from D that is not already marked. So at this time I said, okay, I will mark D, and then, okay, I'm leaving D. And retrace back to the vertex from where I had come, which is F. Again, I ask the same question. Does F has a neighbor? Is G? Very good. Does G has a neighbor? Yes, G has a neighbor, but it's E, and that E has been kind of already marked, right? With C. So there's nothing that I can go for G. So G, we also mark G to be done. We move to F. Does F has a neighbor? No. F doesn't have a neighbor, which is not already visited. F is done. I move to E. Does E have any other neighbor left? And what you will see that okay, E has a neighbor D, but E has been checked. E has a neighbor G that has been checked. So E also doesn't have any other neighbor that is left. So E is also marked. And go back to B. At this point, B will also say that okay, I have a neighbor D, but that is already marked. Have a C that is marked. Okay, done. And here, and then at this point, so B also doesn't have a neighbor. So I back to A and get. So by this is the way we are doing this whole process. Okay. So before I go into details about how we are doing the bookkeeping, is this algorithm more or less clear on the idea that you pick
Yes,
the
sir.
neighbor and go
Yes,
out
sir.
as long as you can?
Sir, I had a question though.
Yeah.
Sir, so in this particular example, if we start from H And
Yes.
with a optimal set of choices, we can cover the whole thing with minimum backtracking.
Yes, that's true. That in fact, I just told that I started with A and it will give me R neighbor, right?
Right.
You could have given me a neighbor T,
Right.
and that could have started giving you a completely different graph. Okay, this set of red edges would be different.
Sir, so my question is is this true that for any connected graph there is an optimal way to do the depth first search like that?
Now there's no optimal sum. Think of it actually, we'll see it, okay? About how much time does it take. Okay?
So starting from different routes and following different paths does not change the time required.
No, not at all. Not at all.
Okay.
Not at all. So for example, let's see, okay, good that you asked this question. Can somebody say how much time does it take? How much time does it take? How many steps have you done? Whatever, and somebody say something.
Sir, in terms of what will the answer be?
Something, think of it.
So we had to visit every vertex once to
Yeah,
mark it
least
red.
once.
Everybody
At
has
least
this
once.
once. That is true.
So actually, we visited every vertex once to mark it in red, and then we visited every vertex again to mark it in green. So
2 times number of vertices.
Yes, 2 times number of vertices, that's true. But then there are a lot of times we visited the same vertex.
Sir,
you realize
I
that.
think-
We are also checking a lot
Like
of.
for example, when I was, look at these things, how many times I have visited B. I visited B when I was from A, I visited C, right? But then
Right.
when I was at C, that time also I found that B is a neighbor of C. So I visited B from C. I realized that B is marked and came back and kind of said, okay, there's nothing to do. But I did visit B. At the same time, when I
Much more
was
than
B,
twice.
I also visited B. I found that B is marked. And so nothing to be done. So the same
Sir, and
vertex.
the edges involved are the edges in some spanning tree of the graph.
Okay, we'll come to that. Okay. But think about the number of steps.
Yes, sir. That is why I'm saying, because the number of steps, if you relate it to the number of edges we have traversed, it is some multiple of the spanning tree, the number of edges of a spanning
No,
tree of
is
this
it?
graph.
Is it? We have also visited B. We have also visited DA. I mean, we visited B. That's why. How many times we have visited B? We visited
So
B
we-
multiple times.
Right.
we
right,
can-
right.
Yes. So maybe if I go back here, you'll understand.
So whenever we reach to vertex and
Think
we
of it
want to
B.
mark it green,
Yes.
which is to completely write it off, then we
Right.
have to compare all it. We have to essentially consider all of its neighbors.
You have to consider all of its neighbors, of course.
So that will be an order of the degree of the vertex complexity.
Your degree of the vertex, right? You're completely
So,
right.
so
Think of it, how
maybe
many times. Let's just keep an eye on B here, okay? Just eye on B. Here I am first visiting B, first one, right? Next time, no. Now at this point C, I am visiting B again, and I don't know whether you can see the color difference, but I am now changing this color of. I mean, this age has been looking C to B.
Yes, sir. We can see that.
Okay, I have visited B. B is marked blue, so B is somewhat visited already. But still, I do visit it. I don't do anything else. It is visited, it is marked blue, so I don't take any action. Okay, I come back, then continue. Again, I visit from D at this point. Okay, so here I have been taking from D. Okay, I again get B. But B is again marked. So I come back. Okay. So you already seen that 3 times we have seen B, right? Then we come back to B. At this time also, we are visiting some more times. So here I am coming back to this one. At this time, I am going to check what are the neighbors of B? The neighbors of B is D. So I'm visiting D from B. I'm finding it marked green, so don't do anything. I go and see C. I find it marked green, so don't do anything. But I am moving, right? I'm still making. So at this time, I am spending 2 steps at B and taking its neighbors.
So every time we were on a neighbor of B, we had to visit B once
Right.
to not reach B.
Exactly.
So
Exactly.
that could become an order of the degree of B complexity. But sir, then there is also a flip side that if let's say we were at E, and before considering going to F, we would consider going to G.
Okay.
And G we find to be free. So then we would not waste time there, right?
No, we are still gone time.
That is what I was saying, that there could be an optimal path.
Okay, so again, let me see. So this will help. So consider any age. How many times have we moved up and down along this age? Say BC. Along this age, how many times have we moved?
Sir, twice.
Twice. When I was at B, later on, I saw so that I went to C and saw C to be marked green. And when I was a C, I went to B and I saw it was to be marked green. Right.
Right.
Even
right.
this red vertex. When I was B, I moved to E and continued something, and later on I moved back from E to B. So along every age, I am moving twice.
So okay, if we consider the edge from B to C,
Yes.
and we would, if we consider the first time this is visited, we look at A goes from A we go to B.
Yes.
Then from B we go to
C.
do we consider from the edge from B to C then after that, or
No,
do we directly go to
depending
E?
on when we are doing it. At this point, we are not doing it at this time.
Okay, so here we just considered E to be the next one,
Yes, next
just
one.
arbitrarily, and
Correct.
then when we got to C, then we considered B,
Then you consider B.
which is
Right.
again an arbitrary choice. We could have considered H here first.
Even if we had considered H here first, right?
Right.
We'd have been to H, right? I would have
Right.
covered H, found that H doesn't have anything else. I would have gone back
Right.
to C. At that time, I would have visited.
And then when we come back to C, we would have visited B. Okay.
Yes.
But sir, here if we were to consider B first, which we did in this run,
Yes.
and then we said, okay, this has already been marked. Then we go to H,
Yes.
and now we backtrack
Yes.
to C, and then again we visit B from C.
No, we don't
So
visit B at that time.
So, but then how do we to mark C green?
So C is not green, but already from the age, I have marked this age.
Oh, you
see
so we're not only marking the vertices, we're also marking the edges.
We'll mark the edges also.
Oh, okay. Okay.
We'll do that. Hook keeping we'll do later. Okay, but we'll mark the edges also.
So
mark do something on the edges.
Okay.
Maybe we'll even remove the edges.
Got it. Right. So in this case, this edge was only considered once then, because
so there is the thing. So we will be talking in the terms of the adjacency list. So the adjacency list, what happens is that out of the adjacency list of the
oh, okay. So you're saying that it's like a double directed edge,
yes.
right?
Adjacency list, there will be a B is the neighbor of C as well as C is neighbor of B.
Okay, so
you
you
remove B
disconnected
from the neighborhood of C.
Okay.
But that doesn't mean that it has been removed from the other side.
Got it. Right. So, sir, you're saying that every step of the algorithm, what we're doing is taking away one of these directed edges, right? So eventually we'll have to take twice the number of edges out.
Right.
That should be the complexity.
Right.
Okay.
Sir, also that edge from E to B,
yes,
can it not be visited more than 2 times? For example, once when we are going from B to it is visited once, then we see that, then we go to H, see that there is nothing more to be done there, so we come back to C, then we come back to E. Now when we are checking for more neighbors, do we visit that edge or not?
So no, we will. So okay, so there are these bookkeeping issues. Okay, so I will go over to bookkeeping issues here very soon. Okay,
Okay, sir.
but basically what will happen is that every edge we will visit once from this end of the edge, one from that end.
Okay, sir.
How the marking and all will happen, I will come to that now. But for now, you guys are convinced about what is going on here, right?
Yes.
That, I mean, you kind of
Yes,
you know
sir.
that you realize what is going on, right? See how we are traversing. That you continue till you hit the dead end, and then you backtrack, and then again keep on searching.
Sir, then DFS is big of n.
It will be before of V plus
So B plus n.
V plus E. Order of V plus E is the number of edges.
Sir, why
You
is
realize
there
that
a
when we talked about the adjacency list, how big was the adjacency list? You remember the adjacency list that we discussed last class?
Yes, sir.
Yes, sir.
How big was it?
big O of V plus E?
Okay. So in terms of this is what we call a linear algorithm. Input is V plus E, and your output is also V plus. Then the algorithm is also takes order V plus E. Anyway, we will come to that V plus E step very soon. Yeah. So somebody was
Sir-
saying something. Yeah. Go
Sir,
ahead.
so just to be clear, oh, sorry,
Yeah. Go
somebody
ahead.
else was saying.
No. You go ahead.
Okay, sir, I was saying just to be clear, in this traversal, while we're laying down the red lines, if we
Right.
go from A to B, we remove the edge that is directed from A to B, right?
Right. That's
And-
what we will be.
Okay, got it. And then while backtracking, we remove the reverse direction edge.
So the backtracking. How do we do the backtracking? That's a very important point, right?
Okay,
How
right.
do you, like when I am at C, how do I remember that I came from E but not from B? Let's start with that.
Okay,
How do we remember that?
So we can remove the edge, I guess,
We can remove the edge of
that we
C
have
to
checked.
B.
Yes, sir.
Yes,
That
we
have
can
not
do that.
used,
That's
but we
one
have
way
checked.
possibly we can do that. But then we have to be a bit careful. Like for example here, right? At this point, sorry, not this one. Say at this point, E, right? I have come from B. I have somehow kind of marked B in some way, right?
Sir?
Now, because I will do a lot of this kind of a traveling.
Sir,
Yes, sir.
Yeah.
So
during the traversal, if we remove any edge, so it might make the graph disconnected, right?
Yes, we have to be careful about what do we mean by removing an edge, right? We will
So
not
we
remove
have-
an edge. It's all about in the bookkeeping. It's the marking in some sense, right? When you are in a maze and you have been given a chalk and you mark a line that okay, this is the place I have been, or this path I have been. It's not like you are removing it; you are marking it. It is a bookkeeping for yourself that I am not supposed to go in this direction because I have already done.
so you're saying that maybe we can let our system have some short-term memory of the previous node
yes,
that we
we will
came.
do that. So that is exactly this is what's called marking. We will color them. In fact, the coloring that you have seen is exactly like that.
All right.
Okay, it's kind of a label, this kind of process and circles and kind of stuff like that. Right. So Yes, so you guys are giving me some ideas about how do you remember the previous one, right? The parent one from where I came, because that is important. As you can see, that we always at any point of time to remember where did I come from, right? Like after all of this thing, I land up in E, and now I have to remember. See, note that at this point, E has come from B, and you should remember that it has not come from B or something like that. So there are other ways of doing it, but one of the beautiful or simple ways of doing it is what is basically now what is in this side here. Okay, so this is what is called a stack. Okay, it's a data structure. It's a stack. Now the basic idea is nothing. You are stacking books, kind of stuff, right? When you stack books on top of each other, when we want to take something, you can always take the top one. So you can always put things on the top, and you can always take it out from the top. So this is what is called a stack. So stack is nothing but it allows you two operations. One is called a push. So you take a stack S and push. So if the stack is here, S say for now, this is S. Okay, and you take X, you put that X on top. That's basically push. And then there is an operation called pop, which basically says that okay, you take the stack X, look at the topmost element, here in this case is X, and it will output X, and will remove this X from here. So this is just an operation that you can do. So if you guys are familiar with C or C++ or whatever, you can try to implement this operation. Okay, I will give you a set of data points, and these are the only things that you are allowed to do. You are supposed to push or pop. Pop will always output the one that has been last put.
So we worked with stacks in the first semester.
Oh, you
in the
have worked
data
with
structure.
stack? Excellent.
Yes, sir.
So you know that. So now what happens if we do stack here? Okay. So as soon as we will visit, okay, so we start with A, and we start with the vertex. Okay. When the vertex have not been completely done, it will be put in the stack. So at this point, we put it in this stack A. Then we go to the next one, we go to B, and we put B in the stack. Then we go to E, we put E in this stack. Then we go to C, we put C in this stack. So at any point of time, I can pop on the stack, and the what we will get is basically where we are now. So if I pop here now, I will say that I have C. Okay, at this point I am at C. So I can pop, I find out C and say, okay, does C have a neighbor? Does C has a neighbor B? Now marking things will come later, okay? But we say, oh, okay, B has been marked already. So fine. Let me go to the next step. Does it have something? Yes, H. So I'll push C back again and push H. So this is where we are at this point, okay? Now note this beautiful stuff here that's happening. At this time, if I pop the top part, I get H, right? And I said, okay, I'm done. H doesn't have any H. So I mark H green. Once I mark H green, where should I be? Now, I should go to its parent or the place from where I came, which is C. But see, magically C is on the top. Okay. Now I pop C, C finds out nothing is there, C is marked. Where should I go? I should go to the previous one. It is E. Magically E is on the top. Now, okay, what about E? I pop E out and I ask, does it have an H? Neighbor? Yes. E has a neighbor, new neighbor, S. So I push E back, push F back, and I go this one. I go to D. At this point, I realize that T doesn't have any other neighbors that is not marked. So at that point, I mark D done and pop the stack. Now where should I go? I should go to F, right? And see F is in the top already. I go to G after that. And G is now on the top. I will see that G is done. And when G is done, I should come back to its parent, which is F. F is on the top. Okay, F doesn't have anywhere to go. See, I should go to E. And see E is in the top. So in some sense, you see that what is happening here is that at any point of time, the top position is telling us where exactly we should be going next. If we are done, then either we continue from there, or we should be throwing away that one and we will come back. That is the parent of what we have just marked.
So the loop invariant is that the top of the stack is the vertex under consideration.
Exactly.
And then if it has any neighbors that are unmarked, then we can push them in, and if it doesn't, then we can just pop it out.
We just pop it.
Right.
And that's it. The stack automatically maintains the previous one. Okay. Is this clear? I mean, I can see. I mean, couple of you are asking questions. The rest of you are not.
We mark an edge gray whenever we encounter that edge 2 times, right?
Yeah. So this gray edge is something that is something. Basically, gray edge means that it is not a part, as somebody was pointing out. Look at the red edges. Okay, so red edges are the edges on which we have actually traversed, or on which we have traveled and found a new place, unmarked place. Okay, so these red edges are what is it forms a spanning tree.
Yes. So as we are keeping this record using that stack, we don't
Yes.
really need different colors to mark the edge that we have visited, right?
No, we don't.
Because we have
But
this
as
stack.
somebody pointed out, that say for example here, right?
So
We'll
have
have
the
to do
stack.
something, for example, like here, say here from C we have gone to B, right? I've visited B. Then I go to H. H is marked, and now I'm back to C. At this point, I don't once again don't want to visit B. Right? I want to kind of say that okay, now I'm done with B. I should not be visiting it. So one way of doing it is that you kind of remove B from being a neighbor of C. Okay? From the adjacency list. Right? So you remember this adjacency list that are there. So here, if I write it here, so there was A, B, C. So inside the C, what all neighbors are there? Let's see. Maybe if I write it, C has a neighbors of D, E, and H, right? So it has a neighbor, say, H, E, and B, right? Now, what happens is that from C, I will first see B. Okay, when I'm at C, what is the neighbor of B? Okay, give me the last neighbor. It's a B. Okay, B is already marked. So I will just remove B. Okay. Maybe the next time I say that, okay, what is the next neighbor? E. Okay, I will remove E. And I have gone to H, right? And since I'm going to H, I will also remove H. So that when I come back to C, I don't have anywhere to go. So H has been cleaned up. So that is how I will be going over. So let me give you this pseudo code, maybe that will help you to then understand it properly. Okay, so this is what we need. Okay, we need this stack, the push and pop operation that we told that you guys have seen already. And here is the pseudo code. I hope that is written correctly. So I will Okay, I'll start from, first of all, I take all of the vertices are, we have a, for every vertex there is a marker, it is called color, and the color has been set to gray. Okay, so at any point of time, I will, so okay, I start with pushing the initial vertex S V in the stack. That is my starting point. Starting point is in the stack, there is nothing but the starting vertex V. Then what do I do? How long should I continue? Till the stack is empty. If the stack is non-empty, I should continue. So while it's non-empty, you first pop the stack. Look at the topmost element in the stack. So that is where I am now. Okay. So what all the things should I do? Okay.
Sir, what is V?
So V is the in this. Yeah, V is the A here for that. So this
Is
is
there some
the,
initialization?
sorry.
Is there some initialization?
This is the initial vertex from which you start. You start a DFS from a particular vertex.
Okay.
Right. So V is just that.
Got it.
V is just the vertex from which you start. Just initial. Now, if I pop and I find that it has no neighbor, meaning I am standing in a particular vertex, that vertex has no neighbor, meaning I'm done with that vertex completely, right? So then I should mark it green and move on. That's it. Okay. If not, okay. Okay, so maybe I. So this is F, this is the rest of the should be else, okay? So meaning that let's say that the neighborhood of U is not empty. That means there exists a vertex, right? So you take one vertex from the neighborhood of U. Now, if that neighborhood of U is gray, meaning that vertex is not marked, okay, we are visited also, then what should we do? Okay, great. So this vertex is not marked. So now I should just nothing. I should just put U back, right? Put U back, put W back, and mark W to be already seen. Right? That's what I do. I colored the word W to be blue. I remove W from the neighborhood of U, so that I have already traversed it once. I am not even thinking about it second time. And I push U, push V, and I select UV. Select UV basically makes sense that I colored that UV. That UV vertex becomes a vertex H for my standing DFS. So actually, it's not written up in the most correct way. Maybe I should try to give some small technicalities of there. Like, I mean, it's just there's some issues with the pseudocode here. Just so if the color is gray, then you do this thing, and if color is not gray, okay, what you should do is that you should remove this neighbor. This one should always be done. Neighborhood of U. So I mean, W should be removed from the neighborhood of U.
So this removal step can come before the if clause, right?
Or it
Take
should
W
come
from,
irrespective of what the answer of the if clause.
right? And then in the if clause, if the color is gray, then we select U comma W. Otherwise, there's no selection, but we still push U and W back into the.
That is no, you push U and W if it is gray. See, if the W
Right.
color is gray, that means here, right? At this point, say. So I'm at C and I got to H. H is
Right.
gray. That means I have not yet seen H. So at this point, what should I do? I put HC back and I put H back.
Correct.
Okay. Now, if it is not the case, if I find B and B is not colored gray, then I should just put C back. That's it.
And remove the edge from C2.
And then move the edge B from C.
Okay.
Okay. So there is some small issues with the pseudocode, but that if you guys have understood it, try to fix it. It's just written in the site. There's some couple of typos here. Okay.
Okay, sir.
So
So we know that any single directed edge cannot be visited twice because we are removing it upon its first time we visit any directed edge. And we know that to make any vertex green, we need to exhaust all its directed edges that are going out of it.
right.
So we know that every single directed edge has to be visited exactly once. So this operation of removing edges is ensuring that it's an order of mod of E, and then mod of V component is coming from the stack makeup, right?
From the stack thing, because anyway, then even if there's no A, you still need E, right? You have to go for all of them.
Right. Even the stack and all the coloring operations,
Right. So
they're all mod of V. Right. Okay.
What about the rest of you guys? I can see that none of you are even answering, so I'm not 100% sure how many of
Yes,
you
sir.
are.
Understood, sir.
Understood?
Yes.
Okay. Okay. If you understand it, that's very good. So do look at some books, whatever books that you have. Everywhere there will be this DFS algorithm will be very well written. The pseudocode will be written particularly. Okay. So go and look at the pseudocode, and there can be small changes in the terminology and all, but basic idea is this. Okay. It is using the stack, you kind of, and the coloring technique, you kind of do the bookkeeping so that you do this DFS algorithm in order V plus. This whole thing is every edge is visited twice. So the total running time is order V plus. Okay. So now let me try to give you a very important, very nice application of this DFS algorithm. Of course, it is useful for what all things, right? So at the end of the day, I run this DFS algorithm on a graph, right? And which all vertices have been colored green? What do I know from this? If all the vertices have been colored green, I know that means every vertex can be reached from a particular that vertex, right? It is connected.
So all the green colored vertices compose the connected component of whatever initial vertex that we found.
All the green colored vertices form the connected component. Right. Also, one thing that is you can see that if at any point of time, okay, so say here at any point, look at the first time or any time, I get to see the first gray for edge, right? At here I am at C and I find that, oh, there is a B, which is already marked. What does it mean? It means that I have come to C from some path and I can reach B from some other path. So that means I can see a cycle. So if I give you a graph and ask you go and find out a cycle, the thing to do is run the DFS. And you will see as soon as you see the first time you see a vertex that is blue in color, you realize that you have found the cycle.
Sir, but if suppose in this run we look at the vertex D, and we were considering its neighborhood, then it considered W, and okay, it considered B, and saw that it was blue. So now we know that it must be a cycle. But suppose that DB was not an edge, DA was not an edge, DE was not an edge,
Right.
and DF was the only edge.
Yes.
So when we are at D, wouldn't we consider F as
So that is a good point. So this is something that we should kind of be careful over here a bit. This was a bit of a, you're right. The way in which it was written that you don't remove F from the neighborhood of D, right?
correct?
Yeah, so that is the only thing that you have kind of keep in track of that.
Okay.
But when you are going to D from F, you might also want to remove the D from.
Because
F
then
from D.
backtracking is, since it has been outsourced to the stack itself,
Right,
so we never need to actually consider this edge.
right.
Okay. Right.
Yeah. So of course, in algorithms, the reason we do this DFS and then we'll do the DFS in a lot of detail is, although these algorithms are very simple, okay, many times the actual algorithms are not a kind of a black box kind of plug and play kind of stuff. It's not like, oh, do DFS and do something. Many times it is tweaking the DFS a little bit. Okay, so maybe you want to store this color, that color, or something like that. Maybe you want to look at some other thing. But the basic idea is similar.
So you're saying that for some other algorithm, we might need to do modifications to this source code of this DFS itself, rather than using it as a module.
Like for example, this circle thing is also, you have to do some small things.
Right. Okay. Got it.
That's why
Sir,
kind of, yeah, go ahead.
Sorry. Sir, I was saying this algorithm seems to be just as applicable even if we were working with a directed graph, right?
Yeah, very good. You just now, yeah. Yeah. The other thing that I will just come to that.
Okay.
And
Okay.
we
Sorry.
will, yeah. So also the other thing is that, of course, we will, the red edges that we have a spanning tree. And also you should kind of, by now you should realize that we have a spanning tree of systems. So this is called a DFS tree. Now this DFS tree has some nice properties, but before I go into that, let me go into this directed. So we did this whole thing for undirected thing, but believe me, there is nothing special about directed or undirected. Both of them have the exact same. So I will do the same run on this graph. Now this time starting from this vertex H and in this directed graph. I start with H. I go to its neighbor, the G. Now I take some neighbor, it has two neighbors, F and E. I pick any one of them, E. Then it has other neighbors. I go to B. Then I go to A. I continue. At that point, I hit A.
Sir, sir, hello.
Yeah, go ahead.
Sir, sorry to interrupt you.
No.
Sir, by the serial code that you have written about DFS, on this GEB should be marked in blue color.
Which one should be marked?
Sir, GEB should be marked in blue color.
Okay, so maybe you cannot see it exactly, but there is a slight difference between the color of this B and B.
Oh, okay. Sorry, sir.
You see the difference, light, and when I'm looking.
Yes, sir. Now I noticed it. Actually, yes, sir.
Yeah, I think there's some serious color differences. Okay, is that fine?
Yes, sir.
So now at this point I am at A, right? And A doesn't have anything. So I backtrack and I colored A, done. Okay, somehow A has some red. So with the same I colored red earlier, B. But okay, forget that. Now I come to B, and then B doesn't have any other neighbor. I mean, B has a neighbor of C and D, but they are not directed neighbors, right? So they're not directed neighbors. So B is done. Now I come to E. Now E has some neighbors, so let's see where E goes. E goes to D. At that point, D says that, okay, does it have neighbors? So yes, D has a neighbor A, not good. I mean, it is already marked. D has a neighbor B, that also is good mark. Right? At the time, so D is also done. I come back to E. At the time, I go to C. Now C has also all neighbors. C has a neighbor B marked. C has a neighbor G, that is also marked. So C is done, right? And we come to E, and then we basically come to G. Then G have another F. We see that F to D, F to E are already marked, and split this back. So it is exactly same as what we did last time. Okay.
So the only thing that needs to be clear is that the neighborhood that we're talking about is the out neighborhood.
It's the out always.
Right.
The neighborhood that we're talking about is the out, not the in neighborhood. In fact, in an adjacency list, understanding the in neighborhood is very hard. In an adjacency list, you always have the out neighborhood.
Okay, right.
So this is basically this DFS of this thing. So now, one thing that you can see that if I draw, if I draw this graph, okay, so if I draw a tree, right? If I draw a spanning tree, okay, so I say I draw a spanning tree, right? So maybe this is kind of spanning tree there. This is the direct spanning tree that I'm talking about, okay? Now there are lots of other edges that are not in this tree, right? For them, they can be edges like this. They can be edges like this. They can be edges like this. They can be edges like this, and so on. Right? Now, can you tell me which of these edges, these four edges that I've drawn, then maybe I'll number it 1, 2, 3, 4, cannot be there if the red, if this spanning tree that I've drawn, the red edges tree, is the
Sir,
DFS tree.
will you kindly repeat that question?
Will I have a what?
Sir, will you kindly repeat the question?
Yes. So so maybe I'll do a poll, okay? So at least some of you can at least participate. Sorry. Can you see my? Let me just stop here. Wait 2 seconds. There's some other thing here. How many of you are 50? So maybe let me share my screen again. So can you see my screen?
Yes, sir.
Yes, sir.
Yeah, my screen. Okay. So the red edges forms a DFS tree.
Sir, did you
And-
give a poll? Because I didn't get any
So I
question.
am not yet given it. Just 1 second.
Okay,
So
okay.
let me explain the problem. Okay. So this is a graph in which the red edges are a DFS tree. Okay. So red edges are the edges that have got after I ran a DFS. Okay. Now
Right.
the blue edges are edges that are not in the DFS tree, but is in the graph. Okay. Now I'm saying is that if these red edges forms a DFS tree, then one or two of them of these edges are not valid. It's not possible. So there are numbered the edges as 1, 2, 3, and 4. Okay.
Sir, could
So,
you please repeat the question? I got disconnected.
okay. So you can see this graph. Okay.
Right.
So say the red edges forms a DFS tree.
Okay.
Okay. And the blue edges are edges in the graph that are not part of the tree.
Okay.
Okay. I'm saying that out of these blue edges, I have made something wrong. Okay. So
Okay.
one or two of the edges cannot be there.
All right.
Okay. So you have to tell me which one.
Okay.
I have done the poll.
Sir,
Yeah.
sir, in this spanning tree that you made,
Yeah.
it's not necessary that we firstly went left or firstly
No,
went
I'm
right.
not saying
There's
any
no
of this.
hierarchy, right? Okay.
Yeah, so let's say that we went left. Okay. So let's say that this is how we went left. In terms of the set of ages discovered is 1, A, B, or maybe, yeah. So let's say that yes, this one was discovered first. This one was discovered first. Then this one was discovered second, third, fourth, fifth, sixth, seventh.
Okay.
So, just to ask,
Yeah.
so our answer should not depend on the path we are taking, right?
No, so this path, so this is the discovery, means the way. So this,
Oh.
so the green one basically says that this. So this is the first one. It started from this one.
Oh.
Okay.
Oh,
The
okay,
next
okay,
one that
okay.
is went towards this. These are the in terms of the gray. When was things become gray kind of stuff like that. Okay. This is the numbering.
Okay, sir.
Okay. I mean, I can see a very slow progress, but that's fine. We'll give another few minutes. Hello. Hello.
Yes, sir.
Yes,
Yes,
you
sir.
are audible.
Yeah, I'm audible, but I'm not 100% sure whether how many of you are actually present. This is very irritating, I must say. There are 23 people who are present. There is me and Omkar, so that is 21, and only 12 people have submitted this one. So I can see that some of you are very interested in this thing, but the rest of you are not interested in the sense that they are just putting it on and just, I think, off somewhere else. I mean, this is just not, I mean, this is quite hopeless, I must say. I mean, if this is the kind of interest that you guys are showing, I mean, then of course, I am not going to consider anything if you guys are now saying that, oh, I am finding stuff on this subject. Who cares? That is not my job. If you are not coming to the class, or you're not listening to the class, not answering the same thing, then I will just figure out those 5 people who are asking me questions or who are interacting in the class, and the rest of you can go to hell. I mean, if this is the level of commitment that I can see from you guys, then sorry, this is something that just, I mean, pathetic. I mean, already I know that there are some 12 people who are not coming to the class. And the people who are coming to the class, even with my request, many requests, none of you even answer or even unmute yourself to even ask us, say even hi or hello, or even ask something yes or no also. And now I realize that when I'm doing the poll that none of you are even answering this question. So that means, I mean, it's not like you are not answering. I'm sure that if you think it, you'll answer. But just you're not there. You've just switched on the Zoom link and gone. Now, I hope that you understand that this is ISI, not some random college. Okay, and in this case, I mean, you are almost paid to learn. It's your responsibility to come to the class and do this work properly. I am happy to teach only 5 people also who are interested. But whenever I find that there are people who are trying to cheat me by trying to kind of act it smart, by saying, oh, we are all there in the class, but actually you are not, that is very, very unfortunate. I mean, all I can say that, okay, go and read this chapter and go. Whoever has any problems can come to me and I will discuss with them. Maybe that's what I should do now, from now. And I will see how many people fail in this class. This is a compulsory course. I will, you will learn it when we record. This is the beginning of the course. I understand that this might not be your most favorite subject, but at least give me some time to explain to you. And if that is the case, just tell the dean that no, we are not interested in this course. We are going off. Perfectly fine. I mean, this is just unbelievable. I mean, when you come to a class, the physical class, things are very different because you're in the class. Then I can at least try to put something in your head. But if you are sitting in a laptop and kept your thing, everything muted and not even listening to what I'm saying, then how can I do anything? I mean, if this is the case, then I am myself going to report to the dean's office. That my mode of teaching will completely be different. There's no more lectures. only those who are interested will call me, and I'm going to interact with them. That's it. I mean, this is just, utter nonsense that you guys are doing here. I mean, okay, since I anyway started it, in the next 2 classes I will do some stuff. After Diwali, we will have completely different way of. There is no classes whatsoever. It will be only exams after exams. I will just tell you all the chapters which you are supposed to study, and there will be exams. That's it. You go and
Sorry,
copy,
sir.
do whatever is best up to you.
Sir,
I mean, whoever have any doubts can call me up and they can ask me, and there's no problem. I will discuss with them completely, with full heart. But people who are not interested, you guys can go ahead and do whatever. Anyways, so for this thing, the correct answer is that three. Three is not the one that cannot be correct. The reason is that since we are dealing with this, so once we go to 2, so the first one is 1, then 2, then 3, then 4, then 5, then 6 is the time when the first time it has been looked into. So that means it has been colored, marked something. So from gray to something else. Okay, I'm not saying it has been colored finally. Gray to something else. Then we come here, you retrace back the path from 6 to along this path, right? We go to 4, then we go to 3, then we go to 4. Of course, at this 4, say for example, we can find that there is an edge here. That's very much possible, right?
right.
And when I'm at 2, I can go down here and it's like, okay, this is the 7th thing that has been looked into, and this is the 8th thing that has been looked into. But at that time, if there was this path, then I would have gone to here, right? And then this would have been the red path, edge, not this. I would have accessed this one first time from 8, not from this side. So this would not have been possible.
Sir, can you please explain why 4 is also not wrong?
Okay, 4 is not wrong because it is it's a directed path, right? When I'm at 6, this one is not a path, it's not a neighbor of 4. Sorry, this one is not a neighbor of this.
So can you number it? I think that will be better.
Yeah, maybe. So I'd say A and B. Okay. B is in the neighbor of A, but A is not in the neighbor of B. So when I'm at B, I don't find A. So B doesn't have any neighbor. Out neighbor is 0. We are only talking about out neighbor, right?
Right.
So I don't access A. So if you can think that okay, this vertex is not there, so this edge is not there. Okay. If this is not there, then what will happen? Then after I have 8, I will kind of go up. Then I will come to here, come once. Okay. Then I'll come to maybe here or maybe here. Then come here. Then come here. Then come here. At that time, I will see that there is an edge from here to A to B, but B is already marked, so that is perfectly fine.
Okay.
So interestingly, even if you haven't mentioned any order
Yes.
of going left first or right first,
Yes.
then we couldn't discount 3 or 4, but we can say that one of these two must
One
be
of
wrong.
them is not. First.
Right.
Yes. And not only that, if you are doing it with an undirected graph, then neither 4 or 3 will have happened.
Oh, right. Because yes.
Then both of them will be wrong, right?
Both
Oh
of
no.
them will be wrong.
No, both of them will be wrong in an undirected graph.
Yes, exactly. Both of them will be wrong.
And in this case, since it is directed, it depends on which one we are going for. Since you took the left half first, that is why 3 is wrong.
Right.
Right.
Okay. So, okay, good. So this is what happens in this case, okay? And by the way, the same thing that you can, using this DFS, you can also, in the undirected graph, you can also, in the directed graph, you can also see that, oh, by the way, I forgot what was I saying here. So, yes, so in the case of undirected graph, so these are called, this kind of undirected graph, these things are called cross edges. These are called back edges. Okay. Sometimes in the case of the directed graph, these are called forward edges. So in an undirected graph, you can have 3 edges or the back edge. You cannot have cross edges.
So any directed graph, if
Yes.
we can think of it as some sort of an ordering, right?
Any directed graph, you can think of some sort of an ordering. Yes, but what kind of ordering?
Some poset, a partially ordered set.
It's a partial order. That's not
Sure,
a total
so-
order.
So you're saying that if we make an edge from something smaller to something bigger, that's a forward edge.
Right.
Something bigger to something smaller, that's a back edge, and then two incomparable edges,
But
and
because that's the-
incomparable
Are
edges.
on different connected components.
But it's not connected component, different. Yeah, different uncomparable. That's what it's saying.
Actually,
Different
sir,
subtree.
That does also mean that they are in two different connected components in terms of the spanning tree, right?
In the sum of the spanning. That's
Right. Okay.
okay.
Sir, in there are only two kind of edges in the DFS tree.
Yes.
Will
Only
you
two
kindly
kind of-
explain this?
Hmm?
Will you kindly explain this?
Yeah, so just like we just explained here, in the if it was undirected, right? So there is only two things edges that can happen, right? The edges that goes from a vertex to its ancestor, right?
The edge number 2 is called the forward edge, right?
Yeah, the forward edge is basically in the case of the directed graph. In an undirected graph, forward and back edge is the same. There is no direction. Right?
Oh, okay.
So there are 3 edges and this is called back edge. That's it.
And sir, in an undirected graph, there can't be any cross edge. Like
There
here,
can
it
be
was
cross
possible.
edges, but not cross edges in one. In an undirected graph, yes. Undirected graph, there cannot be any cross edges.
Okay. Right. So that statement was only pertinent to the undirected graph.
So we cannot have cycles in tree. So
Sorry? You cannot have cycles in tree, that's true.
that's an indirected graph. So
Sorry, I cannot get it. So can you repeat?
it's fine. So I was thinking about something else.
Yeah, so there's no trees in here, but we are talking here not just for the tree, right? The red edges of the tree. Reds of them are the edges of the graph. Okay, so red edges is the spanning tree. Spanning tree, red edges doesn't have, of course, any cycle. But you can have cycles if you add the edges that are in the graph but not in the tree. Okay.
So the final statement is that when we're doing a DFS algorithm, then we are partitioning the edge set into these two categories, the tree edges
Yes,
and the
for
back
the
edge.
case of DFS, on undirected graphs, you have to partitioning into two categories. One is the tree edge, one is the back edge.
Okay.
There is no cross edge in the case of undirected. Okay. So Yeah, in the case of this directed graph, there can be 3 edges. There are back edges. Actually, there can be forward edges also. Then
So this is probably just,
it's a bit wrong here. It should be forward edges and some
so
cross
maybe
edges.
it's, sorry.
Go
So
ahead.
maybe it's a classification not for directed graphs, but for any graph, but with a spanning tree, right?
No. No. General spanning tree can have any kind of it.
So, but given any graph, if we have a spanning tree,
Yes.
then all the edges can be classified into either of these three
Yes,
categories, right?
yes. That's true. All these edges can be classified into 3 cross, back, and forward.
Right.
Any graph with respect to any spanning tree can be written.
Right.
Okay. Yeah, and okay, yes, this is another thing that if back edges exist, okay, in a directed graph, say here, there is a back edge, then you know that means that there is a cycle, a directed cycle. Forward edge doesn't necessarily say that there is a direct cycle, but a back edge says that there is a cycle.
So, but we don't need a back edge to create a cycle, right? We can create a cycle even with cross edges.
No, you cannot.
So
Directed cycle.
what if we were to create an edge from A to B, then B to 8, and then 8 to A?
Can it be there? Let's think of it. What's the problem with this? Can such a cycle exist?
Oh, okay, right. Sorry.
No, it cannot.
Because this edge itself does not exist, right? These 2 edges have cross edges.
Oh, okay.
The wrong direction.
So it is somewhat there's a transitivity that has been violated because of the cycle, right?
Sir, could you explain what he meant by transitivity?
I mean, like,
Transitivity. Okay, sorry.
go ahead. You go ahead.
So what I meant was if we're making an arrow from B to 8, it's like we're saying that B is greater than 8, let's say. So if B is greater than 8 and 8 is greater than A, then B has to be greater than A. And
Yeah.
since we're making an arrow from A to B, then that means A is greater than A, right? So it's like the transitivity relation that we studied in ordering, that is being violated in some sense.
Understood.
But so that would require some argument, right? That
No, but
a cycle
here you
that
don't need you can do this argument, right? But see, if you are only using cross edges, okay,
right.
then if you start from A to B and then B to A to B is going from, say, this subtree of right to left, right?
Okay.
And then some point you move from left to right. But no edges, no cross edges can be there from left to right.
Okay. So how do we formalize this? Because left and right are they?
Left and right are actually formal.
Okay.
Because in the case
we can just use any two symbols like 0 and 1 to encode
no,
them.
yeah, but when you write a graph, okay, so when we write a graph like this, right, so this subtree has a structure in the sense that it is not a, I mean, so you have seen that so any vertex, right, has say, 2 children. This is called the left child and right child. If it has 3 children, it is called the leftmost, rightmost, and the kind of. So there is an ordering of the children of every vertex.
Got it.
Okay, so in a tree, you can look at tree in various ways. You can look at it as this is what is called a ordered tree, actually speaking. Okay, so in which case, so maybe I'm going off the topic a bit here, but this tree different from this.
Right. So an argument would be like if you were trying to contradict the existence of a cycle based on just cross edges, we could say that we can go up to the vertices that are involved. We go up to their common parent, right? Their their nearest common parent in some sense.
Correct.
And from there, if we look at their children nodes, then they would have a relative ordering
Correct.
based on the
They're
DFS.
all their ancestor descendant node will have it.
Right. And then if we are making a cycle from their children, that's equivalent to making the cycle from the immediate children of the common parent. And since they have an ordering, then the cycle can't be complete.
By the way, I mean, I don't know. So, with your discrete math, did you read this thing, something called a Catalan number?
Yes.
Yeah,
Sir.
they were mentioned, sir. Yes.
They are mentioned.
So
What
in
was
some problem.
it? Some problem.
Yes, sir. It's hard to remember which problem.
Have to remember. The Catalan numbers are the sum of is the number of ways you can put zeros and ones, a string of zeros and ones, n zeros and n ones, such that at any point of time, the number of zeros must be more than number of ones.
Oh, okay.
So there are lots and lots of different ways of saying it. Another way of saying it is that you have an n cross n grid. Okay. And you can only walk along the either horizontal grid or the vertical grid. The number of shortest paths from the bottom left corner to top right corner that are there, which will not cross this wall which is on the diagram.
Right. Okay.
So by the way, the number of trees, number of rooted, these are called rooted ordered trees, what we are talking about, okay? It's also equal to that.
So what is a rooted order tree?
So there's a root, okay? Every vertex,
Right.
every edge has a root, so everything is rooted. And the ordered meaning its children are ordered, meaning the left order and right order are different.
Oh, okay. Okay.
Meaning the left order and right order are who?
Means the ordering of the children are matters.
So these two trees that you've made are fundamentally different. Okay.
Are fundamentally different. It's exactly like what happens if you draw a family tree. Have you drawn a family tree ever of somebody? Have you seen a family tree?
Sorry, sir?
Have you seen a family tree?
Yes.
Like
Yes.
In a family tree is ordered. See, your great grandfather possibly has 5 sons. The second son had 3 children, and then the third son has 1 children. That is different from second son having 1 children, third son having 3 children, right?
Oh, ordered in that sense.
Because it's like ordered in that sense, meaning although in the tree structure they look same. So here what is happening? This is the grandparent. Okay, he has 2 sons. The second son has 2 sons. Whereas this person has 2 sons. The first son has 2 sons. Second son has done. These are 2 different family trees. Because the sons or daughters, whatever you say, they are ordered, right? There's the first son, and second son, and third son, and fourth son.
Sir,
Yeah.
given the definition of Catalan numbers that you gave in terms of sequences of zeros and ones,
Right.
it seems to me that this should be the number of rooted ordered binary trees. Am I right?
No.
It can be any number of vertices.
Yeah. Any number of
Children,
anything.
Sure. So given some spanning tree for a DFS, we can consider all its ordered rooted versions, and then we have to see which one could have passed as a DFS tree, right?
And that is
Is-
one thing, but in DFS it's kind of rooted because you always start from a kind of an initial thing, right?
Right.
So what,
Right.
this is whatever I'm saying here has nothing to do with DFS. Basically. I'm just
Okay.
saying that the DFS thing, whatever these trees that are formed, they are all ordered rooted.
Got it.
Okay. And then, I mean, since you guys were asking whether this ordering matters, right and left, so that's why I kind of went into this direction.
Okay.
Hello, sir.
So,
Sir, one of the students, Arunabha Bhattacharya, has been disconnected and he has attended the poll, but he had called me just now, informing me that he couldn't attend the class because
That's fine, okay.
no internet.
Sure. Yeah. So again, I think if you guys are interested, you can take a look at this one. You can just study about cattle numbers. It's a very beautiful topic. It has something like in over 50 different ways of writing the cattle numbers. And pretty amazing thing. So why is the number of rooted ordered trees is same as the cattle number? It's basically you can represent any tree using a 0-1 string. Okay, so basically, so once I give you a rooted tree, there is a way of traversing of a tree using what is called a left traversal or right traversal. So what is left traversal? That at any point of time you move left, just like in the case of DFS, you kind of move. There, this is a left traversal tree, which means that you are at this point, you go to the leftmost node, then if you have nothing else, then you come back. Then you go down again, whatever is left, and then if you have, then you go to the leftmost node, go up, again you have nothing else. So in that case, so let me, if I define, so every action is moving one step down or forward, right? So this one, therefore, is I am going down, I can say 0. I go up 1. Then I go down 0. Then I go down 0. I go up 1, go down 0, go up 1, go up 1. So this tree can be represented by the string which is 0, 1, 0, 0, 1, 0, 1, 1. Note that the total number of things is 2 times n minus 1. Similarly, this
This
one,
makes a distinction between the two graphs that you have drawn on this page, right?
right? Like this graph, how much will it be? You will be going down, right? So it will be first you go down 0, then 0, then you go up 1, then go down 0, then go up 1, then go up 1, then 0, then go up. So this one will become therefore 0, 0, 1, 0, 1, 1, then 0, 1. You see that those strings are distinct. And now if I give you one of those strings, you can easily draw a graph out of it. So it's a one-to-one correspondence. So for example, this one, right? Say maybe this is the graph that case that I'm drawing. 0, 1, 0, 0, 1, 0, 1, 1. Say I just drawn something. What is this? Okay, I am at the vertex. Then 0 meaning I go down. 1 meaning I go up. Okay, now I'm back to here. Then 0, I go down. Then again 0, I go again down. Then 1, then I go up. Then 0, I go down, up 1. You see that there is a connection between this. There is a one-to-one correspondence between strings of this kind and this kind. And
Sir, what are these called? I mean, what is this kind of traversal called?
it's called the left traversal.
Okay.
The left traversal. That's right. But the interesting thing is that can you draw this one? 0, 1, 1, 0, 0, 1, 0, 1.
No,
Sir,
No,
no,
sir.
sir, because
Yeah, go ahead.
By the
Sir,
end of third element, we will have more ones
more
than
one
zeros.
than
Exactly, because I start from here, I go down, then go up, then it says I go up through the root. That is not possible, right? So the important thing that is there is that at any point of time, the number of zeros must be more than more than equal to exactly what I told. This is exactly the thing that happens here. Catalan numbers are a very powerful concept in combinatorics that helps us count a lot of important things, including this very simple and yet very elegant way of counting the number of rooted trees, rooted ordered.
Sir, and that diagram that you had made of with the square and the identity line, that also
Yes.
gives us a way to calculate that, right? Because then here we can use the reflection principle.
You can, yeah. So there is a concept of calculating Catalan number. That's a different issue. Okay.
Okay.
But I'm saying that what is this one? So it's like any path here is a path of horizontal and vertical lines, right?
Right. And here 0 can correspond to the horizontal movement.
0 corresponds to horizontal, vertical corresponds to 1. And the idea is that at any point of time, the amount of vertical that you have gone must be less than the amount of horizontal that you have gone. Right?
Here we cannot touch the red line, right?
So you can touch the line, but you cannot cross it.
Cross. Okay, sir. Sir, don't we solve this problem? I mean, don't we count this Catalan number using some reflection kind of thing?
So there are lots and lots of ways of doing it. Okay, the most standard. So of course, using reflection and all, you can count this one, but those are kind of ad hoc techniques. Okay, the most standard technique is through generating. You have done generative functions in your class?
No, sir.
You have not done generative functions in your discrete code?
No, sir.
But we have learned it ourselves.
What all things are done in your discrete code?
Sir, we discussed mostly graph theory, and the other things were not discussed as much as it should be, I guess.
Counting and all are not there.
So we had some lessons on counting, but not in the generative functions at least.
Okay, so generative function is a very powerful tool, not only just in counting, but in lots and lots of other things. For example, people here, I know many of you are very much into like this counting and all business are pretty stupid. We are only interested in advanced mathematics. So for you guys, I will just say that can you count the number of non-reducible or irreducible polynomials of degree d over fp? Such kind of so-called mathematical step counting, okay, can only be done through generative. Similarly, the same thing about counting various of these young tableaus and all that are referred in the representation theory and all, they can only be done through generative. So generative function is a very powerful thing, and I'm very tempted to give you a lecture on generative functions, but that would completely be out of the topic of calculus.
Sir, can you send us some resources on generative functions?
Yes, maybe that will be something I can do. I can upload some nice articles that are there. It's quite a important mathematical concept. Who taught you when you discrete math?
Professor Shondip Das.
Generative function is not in your syllabus. So is it there in the
Sir,
syllabus?
it was in the syllabus, but it was not covered.
Okay, anyways. So I think I'm kind of done for the day today. There were some parts that was left. So let me kind of quickly kind of tell you what else is left here, and I let you guys go back and think. Okay. Okay, this is running time is fine. So here is the problem. It's something that you have done or you have been discussed in class. Okay. And I want you to think about how to solve it now that you have seen something. So basically, say you have this 8 kind of different work that you have to do, A, B, C, D, E, F, G, H, and then there are some rules. What is the rules? Something like this. That A must be done before B and D. B must be done before C, D, and E. G must be done before E, F, and H. So it's kind of like a poset can think of. Okay, a various not poset but some partial, some incomplete inequalities have been given. Your job is to come up with an ordering.
Sir,
Yeah.
sir, we can do it like in a graph way, where directed graph where A is connected to B and D, and so on, and the ordering of the chart can be given by the DFS.
Okay, so you have given this idea. That's good, but let the other people also think about it. So I will just you're right. So this kind of so first of
Sir,
all,
could you
there's
repeat
2
the
parts to
idea?
the whole problem. Yeah.
Sir, could you repeat his idea?
Okay, I'm telling you. So this has 2 parts to this problem. Okay, so this problem as such has nothing to do with graphs. Okay, but whenever there is some kind of stuff like this, where there are binary relations, you should always think about graphs. So first of all, can we represent this information in a graph? So let's see. So A, I have drawn this kind of an edge. Every job has been represented as a vertex. Now A must be done after B and D. So what I do is that I draw an edge between from D to A and B to. That means A must be done after D, A must be done after B. Now B must be done before after C, D, and E. So that means I will draw an edge from. So it's kind of because see every edge represents a binary relation, and this is what is giving is a binary relation. B must be done before C, B must be done before D, B must be done before E, kind of stuff, right? So similarly, you can do it for all. Like G must be done before E and F. So G must be done before E, G must be before. So by doing so, you can represent this whole information in a graph. This is the graph. Okay. And now what do we have to do? Our job is to kind of come up with an ordering of the vertices, right? So our job is what? Our job is to kind of say something like this. That I want to first say the A, B, A, D, some kind of stuff like that. E, something like that, some ordering, right? G, H, so G, F or something. The idea is that H must be done before B, B must be done before D, and such kind of all the edges must go from left to right. There should
Sir,
not
this
be
was posed as a problem at the last of our last Friday session.
tutorial, right? Yeah, I know.
Yes, sir.
Yeah. So such a backward edge is not allowed. If this is not allowed, that will kind of violate the code. So this is all that we have to do. So once we have this graph, our goal is to find out our order. And how do you do it? Okay.
So also here we can't just start making a tree from anywhere, because we have to be careful where we initialize our vertex, right?
Exactly. So this initialization is not obvious, right? You
Right.
follow them, you cannot start from A. So can you still, from what can you start?
Sir, H.
I mean, H in this case, but in general,
Some sort of maximal element
can you, what is the maximum?
with the. Okay, so then it has to be something that has an in degree of 0.
Which does not have any incoming edge.
Any vertex that has in degree of 0 is a potential starting.
And any starting point has to have in degree 0, right?
Any starting point has to have in degree.
Okay.
So if we don't have any such kind of edge, then we will have that back thing, that back.
Okay, so what happens if you don't have any vertex of in degree 0?
So then there is no such ordering possible.
Why?
Because it is similar to that example where we were violating the transitivity property.
Yeah,
They
or
will be
I can
certain.
tell you in some other way that in a graph, if every vertex,
Sir, it will be cyclic.
yes, there will be a cycle.
You're right.
Every vertex have a in degree positive. Okay. Then there has to be a cycle. Okay, every vertex have in degree positive, I mean non-zero, then it has to have a cycle.
Sir,
So-
then
And a cycle cannot be there because in a cycle, how can we have you do A before B, B before C, C before A? Of course, that thing is not possible. Right? Yeah.
So all we
go
have
ahead.
to do now here is then just identify that maximal element and then create a DFS. And we don't even have to worry about any of the back
If
edges.
you do a create a TFS, then what will happen? What's the big deal? TFS is not giving you an order. TFS is giving you a tree.
Okay.
TFS is just giving you a tree.
So, but with respect to that ordered root tree, we can create an ordering, right?
Okay, good. So this is something I leave you guys think about it. In the case of DFS, let me go back here. See, there are few times, okay? There are certain important times. There are two at least important times. One is called the I. So first time a vertex is colored from gray to blue, that's the initial time, right? That's the
Right.
time. So it's like at time 0, 1, 0, H is colored blue. At time 1, G is colored blue. At time 2, E is colored blue. At time 3, B is colored blue. Time 4, A is colored blue. Time 5, nothing is colored. Time 6, nothing is colored. Time 7, the D is colored. Right? So you
Okay.
can say that you can have an ordering based on, okay,
The time.
when is the vertex color?
Okay.
By looking at the time when it is first colored blue from green.
Right.
Right. So that is an ordering that you can get.
So instead of making the tree and then determining the order, while making the tree, we can also record the order.
Yes, we can do that. But then
Right.
there's another ordering that's also there, which is what? When is the vertex turned red?
Okay.
Okay. A is ordered turned red. Then B is turned red. Then D is turned red. Then C is turned red. So there's an ordering of when it is turned red. Okay, so this is called the finishing time. The starting time of a vertex and finishing time of a vertex. So starting time is the time when the vertex goes into the stack. Finishing time is when the vertex goes out of the stack of the last time.
And is it not necessarily the reverse order?
Nope. Think of it here. I think this example should be safe. Okay.
Okay.
Like say
So
here
we can.
EBA, right? I have an ordering where I first sign E, then B, then A. But look at the
Right.
red things. Red things A, B, but then not E. A, B, then D,
Right.
then
Right.
C, then E.
Okay. Right.
Okay. Now question is that there we have two different orderings.
Hmm.
Which ordering do you choose and why? So the hint is that one of these orderings is the topological. this is your work. Go and think which one is the topological sort.
Okay, sir.
Okay, is the problem clear to everybody?
Yes.
Yes, sir.
Hello. Sir, could you show the question, please?
There is no question as such. So it's like, okay.
I mean those ordering that which work should be done before which.
Yeah. So this was the ordering. Okay.
Yes, sir.
I made this graph of that. Okay. So now you have to give me an ordering of the vertices. Yeah, total ordering of the vertices, such that all of them are kind of satisfied. Which means that there is no edge. If there is a if so here, if this is an ordering, then if you do the work E after H, then it should not be that in some other reason there is a path from E to H backward. That is not allowed. Okay, or there is no backward edge at all. The edges only move forward. In H, do it before D. B before D. B before D doesn't say that you cannot do something in middle. Maybe you can do A before. Okay, but B has to be done before B. So this kind of ordering that you have to find. So this is called topological sort.
Sir?
Yeah.
Sir, I'm just guessing, is it somehow related to queues?
Somehow related to queues? No, it is not related to queues.
Okay.
To explain this topological sort again.
Okay. Say, okay. So I have A, okay, the job. That
Right.
has to be finished before B. Okay. And
So is
so
this
they have to
something
be done.
like a priority queue?
It's a priority queue. Okay, it's a ordering. It's a partial
Okay.
ordering. I'm giving you a set of partial ordering. Okay. And now question that you give me a not a total order, but an ordering of these all the events, such that if something comes after a point, then there is no path.
I think I have a solution. I mean, a method.
No, hold on. So let's first clear up problem. Okay. So I have to do A before B and C. Okay. But I have to do maybe D before C. And I have to do B before so I have to do D before E. And I have to do E before D. Something like that. And maybe I have to do D, I have to do F after D. So one way of writing it is maybe, okay, I can say, okay, I will first do A, then I will do C, then I will do B, then I will do E, then I will.
So that cannot be,
so that
right?
cannot be, right? Good.
So it will be A, B, E, D.
Yes, I have to do B for certainly, then I have to do E, then D, then I can do F, and then I can do C.
Right.
So then what happens when look at these edges? There was an edge from A to C, okay. Then there was an edge from A to B. Then there was an edge from B to C. Then there's an edge from D to F. Then the edge from E to D. And then an edge from B to E. But note that none of the edges are going backward.
Right.
Right.
So we showed that it cannot happen.
Yes. I mean, this is exactly what happens when you do a lot of parallelization. Okay, so you have a, I mean, say you are organizing an event, and you have a group of people whose job is publicity, and there's another group of people whose job is to contact the persons who are performers, and there's another group of people whose job is to print out pamphlets and so on. Now there is an ordering, right? You cannot go and distribute the pamphlet before the pamphlet is produced.
Right.
Is done, right? And you cannot. So there is various kind of ordering that happens here and there. It is maybe you can print the pamphlet and wait for some time and then go and distribute it. That is very much possible. You do not do it immediately, but you have to do it before.
Right.
Is that if you now want to put them in a so instead of doing a lot of parallelization, if you want to do it by a single person, single team, then you have to do the let's first do this, then do this. Now how will you go about it? Okay, how will you lay down the whole stuff?
Sir, if we make a, family tree kind of thing for this question and do the activities according generation after generation, then I think we'll have the solution.
Generation after generation?
That means for the tree
No,
must.
actually not. I mean, generation of generation is a different thing. Okay, it will not work. Okay.
Okay, sir.
Sir, I think
Generation, whatever you are saying, that what that happens, what is called as we will do it in next class. That is called breadth first search. Okay.
Okay,
And
sir.
you
Sir.
do it, you realize you can come up with examples, but that will give you wrong answers.
Okay.
Yes, sir.
Sir, I think my confusion was because, sir, do you know what is the origin of the term topological sort?
That I don't think has anything particularly to do with topology. Called topological sort. It might be have some kind of a geometric reasoning. Okay. Some kind of I don't know honestly. Why is it?
Okay, sir.
Sir, hello.
Yeah.
Sir, will you give any hint for the number 6 assignment question number 6?
What is the number 6?
So the average case runtime should be small of n log n for any comparison based algorithm.
Yes, should not be, right?
Oh, sorry, should not be. Yes, yes.
No, there's no hint. Think. It's not hard.
Sir, for the average case runtime means
What does average means?
so the average case runtime means how to compute such.
I mean, so we have to consider all possible inputs.
Yes, sir, and that.
And the number of steps taken or all.
Unless we know the distribution.
No, sir said that it will be uniform over all possible inputs.
Yes, it's uniform. It's uniform over all of them. Think it in, yeah. Can the average case be very low? If the average is very low, what does it mean?
That for most cases it is taking, it is doing it in only a small amount
yes,
of
good.
right.
You have told the right word. Average is very low, meaning for most it is very low.
Sure. So we'll have some sort of a pigeonhole principle.
No, not. Look at the lower bound technique that we have done for n log n.
So for the worst case.
For the worst case. Yes.
So, but that was an upper bound technique, right?
No, there was
Yes,
lower bound. N log n lower bound, right?
Oh, okay, right.
Think of the n log n lower bound technique, and that technique only will give you. You can give it more of that.
Okay.
Sir?
Yeah.
Sir, and so while writing any kind of pseudo or any kind of algorithm, sir, I just wanted to know how much rigorous should we be? I mean, so while writing the solutions to the assignment, so I was having this problem that.
See, you have to explain to me properly, okay? Now, explaining to me properly is, of course, a very relative term. Okay, pseudocode is nothing but a nice step-by-step way of this. I am not asking you to write something that I will encode in a C program. Okay. So you have to explain me step by step. So if you can tell me, oh no, step 1 do this, step 2 do this, step 3 do this, that's perfectly fine with me. That's a pseudocode actually. If you say that step 5, you run over all of them, all the possible objects and find out this thing, right? That is nothing but a for loop.
Right.
Right. So you can write it in that way, that's perfectly fine. But what is not, I mean, and the other thing that sometimes people do is that write it in a English, right? A kind of a explanation in a paragraph. Now, I am not saying that that is not right, okay? But sometimes that requires some your writing skill, your English explanation skills will come in the future. So pseudocode is nothing. Don't get afraid of pseudocode. Pseudocode is nothing but a step-by-step instruction. It is not a programming thing.
Right. And so we do not need to always write in a pseudocode manner, right? So we can just write in like some steps, like step 1, step 2,
Yeah,
like
I
this.
just know step 1, step 2, step 3 is a pseudocode.
Okay, sir. So in some problems, like problem number 7, I was finding it difficult to write it in a pseudocode manner. So because there are a lot of things to explain, so that's why.
Sure. I mean, you have to explain me this stuff. Okay. So now I mean, pseudocode is nothing but a step-by-step instruction. That's it. It's not a code. It's a pseudocode. Again, that's what I say. But then there might be sometimes that you want to write it in English. That's perfectly fine. If that is.
Sir, aren't there any? I mean, is there any? Formal way to write a pseudocode? I mean,
There's no formal way. It's a pseudocode. It's not a code.
Right. Okay.
It's a pseudocode. Pseudocode is basically a set of instructions written in a step-by-step format. Okay. I mean, you don't pseudocode. The idea is that the algorithm is somewhere, and you do the analysis separately. You don't do the analysis while you are going this whole thing. That's the only thing that you can say.
Okay, sir. Thank you.
Okay, I think that's it for today. See you on.
Thank you, sir.
Thank you, sir.
Yes.
Thank you, sir.